Welcome to today's lecture. Again, let's recall what we learnt in the last class. We learnt about heat engine and refrigerator. We shall quickly recapitulate these two machines before we proceed to the discussion of second law at some length. So, heat engine or refrigerator, the important point is they work in a complete cycle, okay, and whatever quantities I will refer to, heat absorbed, heat released, work done, they correspond to a complete cycle of operation, and they come back to the same point, which means same state with same set of thermodynamic variables. Hence, the change in internal energy over a closed loop is equal to 0, because internal energy is a state function and depends on the state, the thermodynamic variables. So, let us recall heat engine. Heat engine, let me pictorially tell you what a heat engine is. A heat engine works in a complete cycle between two reservoirs. One is hot T1, other is cold T2. This is my working substance, whatever it may be. We will choose ideal gas for some reason, and this is the heat released Q2 to the cold reservoir. So, there exist two reservoirs, one is hot, other is cold, and the working substance operate in a closed cycle between these two reservoirs, absorbing heat Q1 from the hot reservoir, releasing heat Q2 to the cold reservoir. In the process, it does some work W. Okay? Conservation of energy tells us that Q1 is equal to Q2 plus W. Okay? And we define the efficiency of the engine, that is eta, which is W by Q1, that is work done by the heat absorbed from the hot reservoir, and this can be written as Q1 minus Q2 by Q1, or 1 minus Q2 by Q1. Now we asked the question, is it possible I set Q2 is equal to 0? This implies that efficiency of the engine will be 1. Is this a possibility? In that case, I do not need any cold reservoir. My machine will extract heat from the hot reservoir and convert it completely to the work. Question is it possible? I said answer is no. Second law forbids this. So, according to second law, this is not possible, though remember conservation of energy, which is the first law, that is satisfied. Then we talked about refrigerator. Again, I should recall that engine and refrigerator which we are talking about, they are all reversible at the moment. You can have irreversible things which I will discuss at some point, but at the moment discussion is entirely on reversible engine and refrigerator, which means that if I have an engine operate in a reverse cycle, I get a refrigerator. So, what is a refrigerator? Refrigerator works in a reverse order. So, I have again a hot reservoir T1, cold reservoir T2, and working substance which is working in a closed cycle between these two reservoirs. But the difference is it absorbs heat from the cold reservoir remind you, T1 is greater than T2. So, it absorbs Q2 amount of heat from the reservoir T2 and then dumps Q1 amount of heat to the reservoir T1. So, it extracts heat from the cold reservoir and dumps it to the hot reservoir, but to make this happen we have to do some work W on the refrigerator. Okay? Again conservation tells me Q1 is equal to Q2 plus W. Remember, this is how the air conditioners work. If you ever try standing close to the vent of an air conditioner, you will find out it is releasing very hot air. This happens because it is extracting heat from the room and dumping more amount of heat to the outside world, which is my universe. Okay. Now, we define the coefficient of performance phi, which is nothing but Q2 by Q1 minus Q2. Okay. Now, we ask the question, is it possible that I have Q1 minus Q2 which is equal to W is equal to 0? Is it possible? If that is possible, then my refrigerator will extract heat from the cold reservoir and continuously dumping it in the hot reservoir, and I do not have to do any work on the refrigerator. That is possible or not? Again, this is not possible. Second law forbids. So, you see, second law takes us far beyond energy conservation. Energy conservation is always satisfied, but still I cannot have an engine with efficiency 1 or a refrigerator with efficiency or coefficient of performance infinity. Okay? Now, with this, let us proceed to the proper formal definition of second law. Before that, I told you that there is a possibility of having two type of machines. Okay? First one called perpetual motion of the first kind. Historically, physicists, philosophers asked these questions. One is perpetual motion of the first kind. What does it mean? It means, can I have a machine which produces work without the input of energy? I will not provide any heat energy, but still I will keep on extracting work from the machine, and it will be a perpetual motion in a closed loop. Is it possible? It is not possible, because first law already tells us there should be conservation of energy. I cannot generate energy in an isolated system. If an isolated system I have in mind, in that isolated system how can I generate energy? So, question is, first law tells us that perpetual motion of the first kind is not possible. Now come to the second law. It is related to the question whether I can have a perpetual machine of the second kind. What do I mean by that? How it is different from the first kind? It is asking the question, can we convert the entire heat energy extracted from the hot reservoir to work? That means I do not at all need the cold reservoir at temperature T2. I only do have a hot reservoir. I am extracting some heat from it and converting the entire amount of heat to work. If that is possible, then efficiency of an engine will be 1. Okay? Remember, we are assuming cyclic processes, so change in internal energy is 0. So, to have a perpetual motion of second kind, am I violating energy conservation? No, energy conservation is satisfied. Still, I cannot have an engine with efficiency 1. Still, I cannot have a machine which is perpetually working by absorbing heat from a reservoir and converting it entirely to work. Okay? This is not possible. That's why second law takes us beyond the knowledge of mechanics. Mechanics, we said, dissipation less, so I have energy conservation. I have all the processes which conserve energy. Here, in the perpetual motion of the second kind, energy is conserved. Total energy, heat energy, internal energy, and the work done taken together is conserved. Okay? But still, I cannot have an engine whose efficiency is 1. Okay? So, now the formal definition of second law. Second law of thermodynamics can be put in two forms. One form is in the context of engine. Second is in the context of a refrigerator. This is due to two great scientists, Kelvin and Planck. Planck, you also know, the father of quantum mechanics, and the root of quantum mechanics was hidden in the study of thermodynamics, namely the black body radiation. Well, what is Kelvin-Planck statement? It says that no, and this is a very important word, cyclic, no cyclic process is possible whose sole result is the absorption of heat from a reservoir and the complete conversion of the heat to work. That is, efficiency of an engine not equal to 1, rather it is always less than 1. Okay? So, this is Kelvin-Planck statement of second law of thermodynamics. In short, you cannot construct an engine whose efficiency is 1. Okay? This is what I have written here. Efficiency will always be less than 1. Whatever heat you supply, you get less amount of work as the output. Now, Clausius statement. Clausius statement is in the context of refrigerator. No cyclic process is possible whose sole result is the transfer of heat from a colder object to a hotter object. That means I must do some work to make a refrigerator working. Okay? No cyclic process is possible whose sole result is the transfer of heat. That means Q2 amount of heat, if you go back to previous slide, Q2 amount of heat it is taking from the cold reservoir and dumping Q1 amount of heat to the hot reservoir, and Clausius statement says it is not possible without some work being done on it. Okay? And so, no refrigerator is possible whose W is 0. Here W means work done on the refrigerator, and hence I cannot have a refrigerator which is perfect with coefficient of performance tending to infinity. Okay? You can prove very easily these two are equivalent statements. If you take reversible engines, it is very easy to understand. Reversible engine operated in reverse order gives you a refrigerator. So, you can immediately argue for yourself that for reversible engines, these two statements are actually completely equivalent. Okay. Let us now proceed to something which is phenomenal. It is called Carnot engine. Carnot engine is a reversible engine. Reversible, I remind you, all the processes are quasi-static. Quasi-static, and plus there is no dissipation. . There is a connection between the forward and reverse process, which I have explained. Working substance, I told you there should be a working substance. I will choose it to be ideal gas, not necessary. You will soon see it is not necessary, but it makes calculation easier. That is why we choose ideal gas. And I choose 1 mole. Again, you can do n moles, does not make any difference. Again, any engine and refrigerator must work in a complete cycle, and I will again choose 2 reservoirs, hot reservoir T1 and cold reservoir T2. This is the definition of a reversible engine, which is known as the Carnot engine. I will give you one realization of Carnot engine, which uses ideal gas. Efficiency here, because it is non-dissipative, should be maximum, but not unity. That is crucial. This is the crucial point, that even in this ideal situation, efficiency is not unity, but it has a beautiful universal relation which does not depend on the working substance, and it does not depend upon the way you perform your thermodynamic operations. Okay? So, in that sense it is universal. Remember, universal means the efficiency which we will calculate, okay, will be independent of the working substance, and in the order I execute the thermodynamic operations. Okay. Now, this is taken from Wikipedia, which I have clearly acknowledged here. You can see Nicolas Leonard Sadi Carnot. Carnot is the right pronunciation. He was a French military engineer and often described as father of thermodynamics. This is Carnot, who was a military engineer, and he wrote only one publication, and in which he proposed this Carnot engine. His work was more or less forgotten before Clausius and Kelvin, these two names, famous scientists you are already familiar with when I introduced to you the formal description of the second law of thermodynamics. These two famous scientists actually resurrected Carnot's work, and now Carnot is known as the father of thermodynamics, because he gave us a procedure to find out an engine, okay, which could have maximum efficiency, but not one. Okay. So, let us define Carnot engine. Needless to remind, reversible. It involves 4 processes. Isothermal expansion. So, start from the point P1, V1, T1 in the PV diagram. Okay. First, you have an isothermal expansion which takes you from P1, V1, T1 to P2, V2, T1. Temperature is fixed. Second step is an adiabatic expansion which takes you from P2, V2, T1, but now temperature is no longer constant. As I told you repeatedly in the last lecture, that adiabatic process is complicated in the sense all the thermodynamic variables, namely pressure, volume and temperature, they change. So, P2 V2 T1 to P3 V3 T2. Okay. Now, do an isothermal compression. So, go from P3 V3 T2 to P4 V4 T2. Isothermal, that is why temperature is kept fixed, and its compression, so V4 is less than V3 and so on. Finally, complete the process with an adiabatic compression, again P4 V4 T2 to P1 V1 T1. What is important? You started with P1 V1 T1. Using 4 processes, you come back to P1 V1 T1. So, you are doing a closed loop, and remember few statements which I have written below. The processes can be executed in any order. Okay? I am choosing ideal gas, 1 mole, okay, ensuring that initial and final states are the same. So, you come back a closed loop. Here these 4 processes ensure P1, V1, T1 at the final step, and also at the initial step. We shall calculate the work done and the heat absorbed over a closed loop, okay, and the change in internal energy is 0 over a closed cycle. So, I will not bother about internal energy. I will just be considering work done and the heat absorbed. In every process, there is a possibility of change in internal energy. For example, here, and in an ideal gas, internal energy depends on temperature. So, in these 2 processes, internal energy do not change, but in these 2 processes, 2 and 4, internal energy should change in such a way that overall the change in internal energy is equal to 0. Okay? These are all words, but we should actually go to pictures, and I draw a Carnot engine for you. So, this is my PV diagram, PV, this is my initial point, coordinates P1, V1 and T1. I draw 2 processes, okay. You immediately know which one is adiabatic, which one is isothermal, okay. From the slope at this point, you know this is isothermal, this must be adiabatic. If I want to have an adiabatic from here, this is my second point, let us say, which is P2, V2, but T is fixed, T1. So, this is my first process, okay. Here again you know this process takes me to P3, V3, and from the slope again you know that is an adiabatic process which takes me to temperature T2, and finally I do again an isothermal. This 2-point curve should meet here and it should be more symmetrical. I am sorry, the drawing is not perfect, but let me try to make it better. Well, roughly this, you can get better picture in your books. This is a continuous line. So, you see this is an adiabatic process which takes you to P3, V3 and T2 temperature changes. This is isothermal, this is adiabatic, this is isothermal contraction bringing you to P4, V4, but since it is isothermal it is again T2, and then this adiabatic compression brings you back to the initial point P1, V1 and T1. So, please remember this is a continuous curve. I try to make it better, well, probably better. Now, you see the first one, this is your step 1. Two, 3, 4. Let us recall what were our steps. Isothermal expansion, this is this one. Adiabatic expansion, this one. Step 2, isothermal compression, this is my step 3, and then adiabatic compression, which is this one. Okay. Now correspondingly, I draw this basic picture of an engine which we have been dealing with. T1, T2, Q1 heat absorbed, Q2 heat released to cold reservoir at temperature T2, W is the work done by the engine. Look at this. So, I stirred the system in equilibrium with the hot reservoir at temperature T1, then let it expand up to volume V2, okay. Some work needs to be done which we will calculate. So, it expands to the volume V2, but thermally in equilibrium with the hot reservoir at T1, okay. I will calculate the work done, etc. But it is very simple to realize that it is in thermal equilibrium with T1 and goes from volume V1 to volume V2. That is why I call it expansion, and this is the heat absorbed in this process, Q1. Okay. Now, this process is adiabatic. You know, by looking at the slope, this curve should be very symmetric, which I couldn't draw. Now, you see this is adiabatic. So, in this process there is no heat absorbed, okay, and this process takes it to P3, V3 and T2. So, it comes to the temperature of the cold reservoir. Now, it starts dumping heat to the cold reservoir. I allow compression up to volume V4. In this process, Q2 heat is released, and then finally this process, adiabatic process, brings it back to P1, V1, T1, the initial state, and the cycle continues. Cycle continues. Okay. So, you see, started with P1, V1, T1 in equilibrium with the hot reservoir, then there is an expansion followed by an adiabatic process which takes temperature to T2, which is the temperature of the cold reservoir. Then I allow a compression which brings it back to the volume V4, then one more adiabatic process, okay, this to isothermal, and then finally an adiabatic process brings me back to P1, V1, T1. These two processes, temperature is fixed. Here it is the temperature of the hot reservoir, here temperature, step 3, temperature is that of the cold reservoir, and 2 and 4 naturally being adiabatic, there is no heat exchange, and this cycle continues. I will calculate now the efficiency of this engine and show it depends only on T1 and T2. To calculate the efficiency of this Carnot engine, I have to calculate the work done and the heat absorbed or released in every process. In the case of work done also, we have to be careful whether work done is on the system or by the system. By the system is positive, on the system is negative. Let us proceed. So, first step, step 1. Step 1, what was that? Let us go. This is the step 1. It is isothermal expansion. We have already calculated in gory details what is the work done. Work done is this, and you can see from this picture, okay, V2 exceeds V1, V2 is greater than V1. So, this is of course a positive quantity, so is heat absorbed. So, Q1 is also a positive quantity. So, as I tried to physically argue that here system does some work and absorbs the heat, an amount of heat which is Q1 from the hot reservoir. Okay. Second process, Second process is adiabatic expansion. Okay. So, this is my process number 2. In this process, Q2 is 0. Obviously, it is an adiabatic process, and we calculated the work done, if you remember. This is the work done. In this process, there is a change in internal energy. I recall delta Q is 0, but delta W is minus of du. Okay? These are all finite processes though. So, this is the work done which I can calculate. Q2 is equal to 0. No heat absorbed. Let us go to the third process. What was the third process? Third process is here. I am doing an isothermal compression. Let us calculate what is the work done. Same expression as the previous one, this one. Only thing, here I am going from V3 to V4. This is V3, this is V4. Well, so it should be V4 by V3. But remember, as you can see from this picture, V4 is smaller than V3. So it comes with a negative sign, where this thing is positive, this sign is negative. That tells me work is done on the system and system releases heat. So this is releases heat. Where? To the cold reservoir, which is at temperature T2. These temperatures T1 and T2, they don't change because I have assumed my reservoirs are very, very big. Here this is heat absorbed, here heat released, and these 4 taken together gives me the net work done, and net change in internal energy is 0. In this process, there is some change in internal energy which is compensated by the equal and opposite change in internal energy in step 4. Okay. Here also it is an adiabatic process. So, delta W is equal to minus du, and the du is equal and opposite in process 2 and process 4. Now, we have got everything. Can we calculate the efficiency of the Carnot engine now? We can do it very easily. Actually, we do not need to bother about the work done. We can proceed simply this way. Efficiency of a Carnot engine is work done by Q1, but conservation of energy tells me W should be equal to Q1 minus Q2. If I use this, though I have calculated the work done, this work done is not at all necessary for my purpose. All I have, eta is equal to Q1 minus Q2 by Q1, which is equal to 1 minus T2 by T1 log of this and log of this. How do I get this? I simply get this using this expression and this expression. Once I use these two expressions, I immediately get this result. But now there is a problem. Problem is, this expression is too complicated. Here it involves all the values that volume can take in a closed cycle, that is V1, V2, V3, V4. The expression gets simplified only when I can get rid of this and express them in terms of the temperature. That is quite easy, because these two processes, apparently they play no role, because I am calculating Q1 which is involved in this process, I am calculating Q2 which is involved in this process. So apparently these two processes are not being useful, though they are necessary to come back to P1, V1, T1 at the end of the complete cycle, but they do indeed play a very crucial role, which I will show here. You see, adiabatic process connects two paths, right? Step 2 and step 4, two processes. Now, in an adiabatic path, we always have PA, VA to the power gamma is equal to Ca, that we have repeatedly discussed. Now you see that it is an ideal gas. So, Pa Va must be equal to R Ta 1 mole, that is why no N, always on an adiabatic process. So, I can substitute for P in terms of T here. I can completely get P out of this equation and write the adiabatic path in TV plane, if you like, as Ta, Va, gamma minus 1 is C, C is some other constant, some other constant. Okay? So, you can immediately see that I can write PV gamma is equal to constant also as T V gamma minus 1 is equal to C. So, I was drawing always PV diagram, and this is my adiabatic path, say PV gamma is equal to constant, which is also implying that if I calculate temperature at every point, T V gamma minus 1 is also a constant. Okay? T V to the power gamma minus 1 is also a constant, not the same constant as Ca. So, now go back. These two paths, this connects V2 T1 to V3 T2. So, I must have this relation T1 V2 gamma minus 1, T2 V3 gamma minus 1. This should be always true on this path, which I designated by step number 2. Now go to step number 4. What do you have? V4 T2 is connected to V1 T1 also through an adiabatic path. Okay? So, I must be having T1 V1 gamma minus 1, T2 V4 to the power gamma minus 1. So, this is corresponding to step 2. This corresponds to step 4. Why it is useful then? You can easily see it is very useful. Now I can write using this equation, easily write V2 by V3 as this, V1 by V4 as this. Once I have this, what do I have? I have here V3 by V4 and V2 by V1. Okay? What I can do? I can substitute everything. So, you can see from these two equations, I can immediately conclude V3 by V4 is equal to V2 by V1. So, once I have this, V3 by V4 is equal to V2 by V1. When I consider these two equations together, you can immediately see that V2 by V3, or I can write V3 by V4 is V2 by V1. I substitute it back here. Immediately I get efficiency is 1 minus T2 by T1. This is a fantastic result. You see, efficiency of a Carnot engine is only given by T2 and T1. What is T2 and T1? I recall, T2 is the temperature of the cold reservoir, T1 is the temperature of the hot reservoir. It depends on nothing else. It does not depend on whichever way I carried the process through. All I used, I calculated eta through Q1 and Q2, which I have learned by heart how to calculate. Then I ended up with a problem that involved V3, V4, V2, V1. Okay? That means all the values volume can take in a complete loop. But that does not stop me, because I know step 2 and step 4, they are both adiabatic processes. In adiabatic process, PV gamma is constant. For an ideal gas, I can always change it to T V gamma minus 1 is equal to constant. Okay? immediately two adiabatic processes. Step 2 gives me this relation, step 4 gives me this relation. I immediately get V2 by V3 and V1 by V4 in terms of temperature only, and that gives me immediately V3 by V4 must be equal to V2 by V1. If I substitute it back to here, this expression substituted back to here, I immediately get what is the efficiency? It is 1 minus T2 by T1. So, it does not depend on the process, the way, the order in which I have executed my thermodynamic processes. Now, question comes, it is always less than 1. Why? If you want it to be equal to 1, you must have T2 is equal to 0, but you know absolute 0 cannot be reached. We know we cannot reach the absolute 0. If I cannot reach absolute 0, I cannot have a cold reservoir which is at temperature absolute 0. If I cannot reach absolute 0 and I cannot get a cold reservoir which is at temperature absolute 0 in Kelvin scale, as we know it is cannot be reached, then I cannot have a Carnot engine with efficiency 1. So, a reversible engine, I will always have efficiency less than 1. This tells me whatever was the statement of second law of thermodynamics in Kelvin Planck form. You can similarly run the Carnot engine in refrigerator form and reach the similar conclusion. It stems from the fact that you cannot reach absolute 0, and then you cannot have an engine whose efficiency is 1. You cannot have a refrigerator whose coefficient of performance is infinity. Well, this tells us lot about Carnot engine. Later I will also calculate this efficiency using some idea called entropy, which is an extensive variable, and something called TES diagram. So far I have been talking about PV diagram, and if you know the equation of state of the gas, you can immediately construct the VT diagram or PT diagram given your PV diagram. Okay? But I will introduce a new extensive variable which is called entropy and state to you the second law of thermodynamics using the concept of entropy and redo Carnot engine for you and arrive at the same result for the efficiency. Okay? Now, let us propose something which is known as Carnot theorem. Given two heat reservoirs, a Carnot engine, reversible engine, has the maximum efficiency. Okay? Soon I will try to elaborate this first part of Carnot theorem, okay, using some special setup and arguments. Second part of the theorem says efficiency of all reversible engines working between two given reservoirs, that means T1, T2, given two heat reservoirs, that means fixing T1 and T2. Similarly, efficiency of reversible engines working between two given reservoirs, fixing T1 and T2, is the same, okay. These are two parts of the Carnot theorem, okay. But what is more important in the second part, regardless of the working substance, it does not matter whatever you choose as the working substance. I have chosen ideal gas, but one could have chosen Van der Waals gas, but efficiency does not change. That simplest universal form of efficiency, T2 by T1, it really does not change. And regardless of the working substance employed or the operational details, which means, as I have been repeatedly telling you, this means the order in which you perform your Carnot cycle is not important. For example, one could have started from here, P3, V2, T2, or from here, or from here. It does not matter which order you perform the operations, efficiency will be again 1 minus T2 by T1, and always less than 1 because T2 cannot be absolute 0. Well, then you can ask me, why are you choosing ideal gas? Because it is very easy to calculate all these work done and heat absorbed. We have done it at length in our previous set of lectures. We know them by heart. It is very easy. What makes it easy? That specific heat is independent of temperature. If it is a monoatomic gas, which I am always considering, it is 3 by 2 N Kb, which is Kb is the Boltzmann constant. So, you see it is independent of temperature. Well, can I do similar calculation for van der Waals gas? Yes, you can do that, but van der Waals gas will be complicated. Here Cv is a function of temperature. If you assume that, still life is not very complicated, but it could be a function of volume also. So, equations and calculations become complicated. That is why we stick to ideal gas, and believe me, the efficiency does not matter, it is always determined by temperature of the hot reservoir and the cold reservoir. Okay? With this, I will try to prove for you, okay, one part of the Carnot theorem. Okay? What is that part? That part is that if I take a reversible engine and an irreversible engine which has dissipation, okay, then the reversible Carnot engine will always have efficiency higher than the irreversible engine. This part I will try to prove for you, rather argue. In thermodynamics, the beautiful thing is it is mostly based on arguments. It is not very mathematical. All we have used mathematics so far are differentiation, and sometimes not mentioning I have used partial differentiation. Okay? So, what is the idea? Consider a Carnot engine C which is operated as a refrigerator, which is very important. The Carnot engine is being operated as a refrigerator. An irreversible engine I, Carnot engine is denoted by C here, irreversible engine is denoted by I, which is here. Okay? Both are being operated between a hot reservoir temperature T1 and a cold reservoir temperature T2. Same two reservoirs. This is important because the Carnot theorem always mentions given two reservoirs. That means fixing T1 and T2. If you change reservoirs, change the temperature of the reservoirs, Carnot theorem does not hold true. Or to be precise, you cannot talk about a Carnot engine. Always you have to operate your engine and refrigerators between the same two reservoirs. Okay. So, remember, first I have a Carnot engine, this is C. This Carnot engine is being operated as a refrigerator. So, let me first focus on this hot reservoir T1 and this Carnot engine which is being operated as a refrigerator. What will it do? It will dump heat to the hot reservoir. Let us say this is Q1, and since it is refrigerator, second law already tells me that I have to do some work on it. It's W. Then how much heat it must take from here? Conservation tells me that will take a heat Q1 minus W. So, this is a Carnot refrigerator. Carnot refrigerator. Well, what does it do? It absorbs this amount of heat from the cold reservoir, which is Q1 minus W. W amount of work is being done on it, and it dumps Q1 amount of heat to the hot reservoir, which is at temperature T1. Now comes the irreversible engine. Okay? Both of them are working in a complete cycle. Please remember, it is absorbing a heat Q1 from hot reservoir. It is giving out a work which is W prime, and conservation tells me it must give Q1 minus W amount of heat to the cold reservoir. So, this is my irreversible engine I. So, this is irreversible and this is engine. This is being operated as an engine. You can see it takes Q1 amount of heat from the hot reservoir, giving out W prime amount of work, and rest of the heat Q1 minus W prime is being dumped to the hot cold reservoir at temperature T2. Now, the Carnot one is being operated as a refrigerator, takes heat Q1 minus W from the cold reservoir, W amount of work is being done on it, and Q1 amount of heat it releases to the hot reservoir. So, now we look at this composite system. Let me tell you, the most of the arguments of thermodynamics are based on this composite system structure, and hence the having two reservoirs same is very important, otherwise these arguments do not go through. So, look at the composite system and let us assume W prime is W and ask the question, is it possible? What is W prime? W prime is the work done by the irreversible engine. What is W? Work done on the Carnot refrigerator. Okay? To ensure that Carnot refrigerator releases Q1 amount of heat to the reservoir T1, whereas irreversible engine extracts Q1 amount of heat from the hot reservoir. Question is, what is the composite system? Okay? In a closed loop, what is the change in hot reservoir? Okay? Q1 heat is released by the Carnot and Q1 heat is extracted by the reversible engine. So, net change in hot reservoir is 0, no change, no heat absorbed, no heat released. Now, heat absorbed from the cold reservoir, let us see. Okay? This is absorbed Q1 minus W by the Carnot refrigerator. This is released to the cold reservoir by the irreversible engine. So, to the cold reservoir, this amount of heat is released, this amount of heat is being extracted from him. So, what is the net? Net is this, heat absorbed from the cold reservoir. It is absorbed because I have assumed W prime is greater than W. So, this fellow is greater than 0. Well, what is the net work done? That is very simple. W prime is the work done by the engine, should be positive. W is work done on the Carnot refrigerator, that should be negative. So, this is the net work. So, what is the heat absorbed? Okay? heat absorbed is this from the reservoir at temperature T2 and net work is this. Remarkably they are same, and you know it is not possible. So, the composite system is actually like an engine which absorbs W prime minus W amount of heat and converts the entire heat to work. Is this possible? No. Second law of thermodynamics says this is not possible. Okay? Second law of thermodynamics tells us this is not possible. I cannot have an engine which extracts some heat from some reservoir. Here the reservoir at T1 plays no role because no heat absorbed from it or no heat released from it in total. So, what we have, net work is equal to the net heat absorbed from the reservoir at temperature T2. So, this is an engine that violates second law. So, it violates second law, which means W is always greater than W prime. Otherwise, I will violate second law. This implies W by Q1 is greater than W prime by Q1. What is this quantity? This quantity is nothing but the efficiency of the Carnot engine when it is operated as an engine. And what is this quantity? This quantity is the efficiency of the irreversible engine, which I am already using as an engine. Remember, there is a crucial point. W by Q1 is the efficiency of the Carnot engine, which in this argument I used as a refrigerator. But if I operate a Carnot engine as an engine, then I know this is the efficiency. My mathematical arguments tells me that this quantity is greater than this quantity. So, efficiency of a Carnot engine must be greater than the efficiency of the irreversible engine. So, this is the point I will stop the lecture today. What I have discussed, I have told you about the possibility of perpetual machines of two kinds. First kind is forbidden because it violates energy conservation. That means the first law of thermodynamics. Second one is violated because of the second law, and then I showed to you that efficiency of an engine is maximum for a Carnot engine, and that has a universal form which is given simply in terms of the temperature of the cold reservoir T2 and hot reservoir T1. So, efficiency of a Carnot engine is simply given by 1 minus T2 by T1, and this is the maximum. Take any, its efficiency will be less than that of the Carnot engine. Furthermore, efficiency of a Carnot engine will never be equal to 1. That demands T2 should be equal to 0, which means that I must reach absolute 0 temperature, which I cannot, and hence efficiency of a Carnot engine, or for that matter any reversible engine, will always be less than unity. This is a fundamental law of nature. So, this is where I will stop today's lecture.